Welcome to another work problem from Work and Energy. Um, in this example, we're going to be looking at a spring. Now, the important thing, if you recall, with springs is to remember that work or energy that can be completed by a spring is dependent upon the change in length. So if we recall, the work that a spring can do is equal to 1/2 K multiplied by the change in length. In this case, we'll just refer to it as an X length, even though in this case we're talking about a vertical height change, so we could refer to it as a change in Y. But what we want to look at is the idea that we're looking at the square of that change in length. Now, the important part we want to refer to is the fact that we want to look at how that compares based off a nominal length. So first things first, we want to look at what is our change in length or our compression or stretch from the nominal length or unstretched length of a spring initially. And in this case, that is that the change in length that we have present initially is that we were told that the spring has an unstretched length of 40 centimeters. If we work in meters, we want to make certain that we recognize where we're at. So we have X nominal, which is 0.4 meters. And so what we have is our initial length is this 0.4 minus the 20 centimeters of length that it starts at, so 0.2. If we look at that, we have that our initial change in length of the spring or compression or stretch of the spring is 0.2 meters. Our change in X final is the 0.4, the nominal length, minus, again, the 0.3, so that we have that this is now only a compression of 0.1 or 10 centimeters. Now, the reason that we want to look at this more specifically is the fact that what we want to look at is, remember, we can also refer to this as potential energy of a spring. They can be used one or the other depending upon what we're looking at, if we're looking at this in our case. So the potential energy or work that a spring can do, again, is 1/2 its spring constant multiplied by the length in comparison to the nominal length squared. So if we recall, what would we expect the final velocity to be? So if we go into conservation of energy viewpoints, we can have that the kinetic energy initial plus the potential energy initial is equal to our kinetic energy final plus our potential energy final. And I did forget to include on the left-hand side plus the work to go from initial to final. What we want to be looking at is the idea that initially it is at rest. So initially there is no kinetic energy. It is equal to 0. We have an initial potential energy. We're told it is at a height of 20 centimeters. So our potential energy is a combination of both spring and potential energy due to gravity. So we have potential energy due to gravity initial that is equal to mg times the height initial. we have a potential energy due to gravity final, which is equal to the mg times the height final. And we're looking at the idea that there is a motion, or therefore a velocity at the end. So what we're looking at with this is the idea that a potential energy initially is this mg times the height initial plus 1/2 k times delta x initial squared. The work to go from initial to final, because we're treating the change in elevation as a potential energy due to gravity, and we're looking at any energy change due to the extension that the spring is experiencing as potential energies, we can safely say that there is no external loads, external forces acting outside of the gravity and the spring. So there is no work to go from the initial to final states. So this is equal to our kinetic energy, and our kinetic energy equation is 1/2 mv squared. We'll leave this as listing as a final velocity squared plus our mg times our height final plus our 1/2 k times this delta x final squared. Plugging everything in now, we have a 1/2 kilogram, so we have a 0.5 kilogram block. It is moving with G being equal to 9.81. Height initially is 0.2 centimeters. That is plus our 1/2. Our K value was given as 120 Newton per centimeter. So we do want to acknowledge that with that, our K value being equal to 120 Newton per centimeter will require us to multiply by 100 in order to get it into newtons per meter. So that is equivalently 12,000 newtons per meter. So now that we've done that, this is 12,000 newtons per meter. We have this multiplied by our x initial, which was 0.2 quantity squared. That is equal to 1/2 our 0.5, our v final squared, plus our 0.5 times 9.81 times 0.3. Our height is now at a height of 30 centimeters, so 0.3, plus our 1/2 12,000 newtons per meter. And now our final change of spring compression is now only 0.1. As a result of this, we can now reduce, combine similar terms, subtracting over the 1/2 12 times the 12,000 times the 0.1 squared, as well as the 0.5 times the 9.81 times 0.3. Bring that to the left-hand side, multiply by 4 because we have two 1/2, so we have essentially 1/4 times v final squared. So we multiply it to the left side by 4 and take the square root. And what we find is the final velocity is equal to 8.37 meters per second. Hopefully, again, this helps to clarify some of the parts that you've been learning in class with regard to how springs and changes of elevation create potential energies due to changes of gravity, or not changes of gravity, due to gravity, due to a change of height, as well as how springs have potential energy due to a change in its length compared to the original nominal length. And how, as a result of conservation of energy, we build up speed, in this case, where we have a velocity that we can expect at the final velocity state to be the 8.37 meters per second. Thank you.